Well, it says it's broadcasting. Hello, everybody.
Yeah. So we had 230 people register. So
Well,
hopefully we'll have a full crowd.
hopefully.
Okay, so I think we're at about time to go. So hello and welcome everyone to our SLDS monthly webinar. My name is Jamie Spicer. I'm an assistant professor at Wake Forest School of Medicine, and I'm organizing this webinar series, which is sponsored by the section on statistical learning and data science of the American Statistical Association. This is a relatively new webinar series, so if you have any suggestions or feedback, please let me know. I'll put my email address in the chat box, so you can shoot me an email if you have any feedback after this webinar. Today, we are honored to have Dr. Beth Wolf talk about variable importance measures in machine learning. Dr. Wolf is an associate professor in the Department of Public Health Sciences at the Medical University of South Carolina. Dr. Wolf's talk will be about an hour long, so please hold questions until the end of the talk. We should have about 30 minutes left for discussion. And for those of you watching, and if you hear something really interesting and want to go back to it later, we are recording this, and we'll put a link to the recording on our section website under the meetings tab following the presentation. I'd like to thank our speaker, Dr. Wolf, and the sponsor of this webinar, the Statistical Learning and Data Science section of the American Statistical Association. With that, Dr. Wolf, I'll turn it over to you.
Okay, I appreciate that, Jamie. And everybody, I apologize. My camera, for whatever reason, doesn't want to cooperate with the Zoom webinar platform today, and so you can't see me. But that being said, we'll still have a good time talking about all this stuff anyway. So as Dr. Spicer kindly pointed out for me today, I'm going to be talking about variable importance measures and interpretable machine learning. This is something very near and dear to my heart, so a lot of my research focus is on prediction modeling and on variable importance and interaction importance, and in particular machine learning settings. And so this is something that I really enjoy talking about. From a standpoint of the general statisticians and data scientists in the audience, of course, we like machine learning because it offers us alternatives in our toolbox to traditional statistical approaches that we might use for things like prediction modeling. We're just discovering patterns in the data. But of course, a lot of us collaborate across different fields and with people that are not necessarily versed in statistics and certainly not versed in machine learning. And one of the major hurdles that we face in using these approaches is the fact that they seem to, for the most part, they seem to outsiders to be black box methods. And I will say some are more black box than others, but it certainly presents a stumbling block in using these approaches to apply to real world data sets. Oop, now I got to get my slides to actually move forward. Okay. So again, we're focusing today on the idea of machine learning approaches. And so we're focused more on not so much on the fitting of the models, but on how we evaluate importance of individual variables when we're fitting the models, and on visualizing the models. So ways that we can use information about the model to provide a visual for a collaborator to understand what the model might happen to be doing. So it helps sort of ease their comfort level about the model. We're going to be discussing only supervised learning approaches, and in particular, just sort of the more popular, common, and readily available ones. So I'm focused today on neural networks, decision trees, ensembles of trees, and support vector machines. What this talk is not is a comprehensive overview of all of machine learning and all variable importance measures, because we simply don't have time. So we are going to be focused on those more common importance measures that are out there and available that have been evaluated in the literature. I will point out as I go through the talk that there are other things that have been developed, and that this is an extremely active area of statistical research. So just being aware of that as we go through the talk, that if there's one that you happen to know about that I don't mention, it's not that it's not out there and important, it's just I'm sort of having to pick a subset of these things to think about. So going back to our whole focus on the idea of machine learning, if we think about it, we're so used to fitting, we're all classically trained in fitting things like regression models. And in theory, standard regression techniques that we use are machine learning approaches, particularly when we put them in something like a multivariable setting, where we're having to sort of identify these linear relationships across a number of variables between some outcome Y and a set of predictors X. And in that case, we're discovering a linear pattern, where machine learning extends that idea of defining these linear patterns in the data to discriminate some outcome Y to the case where perhaps it's not linear, or we have some strange underlying pattern that we want to find. And common examples of supervised approaches include things like making predictions about an outcome or identifying key features, which of course is the focus of today's lecture. So as I said, regression could be thought of as a machine learning approach. And the thing is, it does have some very nice features. So clearly, one of the things that we like about regression is the models themselves are very interpretable. So the collaborators that we have are often very familiar with them. I clearly work in the world of medical statistics, and physicians and clinicians and even basic scientists are often very comfortable with the idea of regression models and like the fact that they can interpret them. Of course, the caveat is, number one, we lose the interpretability when we try to move machine learning, and so that makes clinicians hesitant. But the regression approaches themselves make very strong assumptions. So of course, we're assuming that we're linear in some logit, in some length function with respect to our outcome Y and our predictors X. We also make assumptions about independence of predictors and independence and things like that. And so when those things are violated, sometimes regression methods break down, and either our inference is inappropriate or our prediction performance is poor. And so they aren't necessarily the catch-all for everything that we might want to do. Of course, machine learning approaches allow us to relax some of those assumptions that we make when we do regression-based approaches. So for instance, like they're able to capture nonlinear relationships between our outcome Y and our features X without a priori specification. It's not that we can't do that in regression, but we have to specify a priori. They often are also better able to handle large numbers of predictors. So if we start thinking about moving into the world of informatics and omics data, then clearly we can have issues where we have lots and lots of predictors and a small number of observations. And a lot of the machine learning methods do a little bit better job of handling that than the traditional regression approaches. But as I've commented multiple times now, the approaches themselves don't provide a direct interpretation of the impact of any one individual predictor on the outcome. And this is where we tend to lose collaborators. So they get frustrated that they see that the prediction model is doing a great job of predicting, but they want to understand how the individual predictors are contributing to that prediction. And so our goal today is to think about some ways that we might elucidate that information so that a clinician or a collaborator would be a little bit more comfortable with us using machine learning approaches. And then for, again, opening up this broad variety of tools that we could use in fitting a prediction model. So I work in the world of biostatistics, and for my students, both my clinical students and my PhD students, I often find it's helpful to put things in a context. So throughout this talk, I'm going to be putting this in the context of a specific clinical example. In this case, we have patients newly diagnosed with lupus nephritis, and we're looking at their treatment response at 1 year. So we want to know whether or not, based on some baseline characteristics and and the treatment that we're giving them, can we predict how likely they are to respond at 1 year? To know whether or not we think we're going to be successful. These patients are already relatively sick, and we don't want to make them any worse with cytotoxic treatments. So the data itself, it's a relatively small data set, which makes it a little bit easier to present for what we're talking about today. But of course, we have treatment response, yes, no, and that's our outcome. We have demographic variables, age and race. These are lupus patients, so they're predominantly female. So we don't actually have sex because this is an entirely female population. In typically trying to understand how likely somebody is to respond to treatment in lupus nephritis, we have traditional clinical markers all shown. I think I can put my mouse here. All shown here. So C4 complement, double-stranded DNA, estimated glomerular filtration rate, urine protein to creatinine ratio. These are sort of the traditional approaches. And then we have some urinary biomarkers. These are all inflammatory cytokines. And again, trying to sort of show the level of inflammation in the kidneys at the time of diagnosis, which we would expect would tell us something about how likely somebody is to respond to treatment. And so the secondary question of this particular, the overall goal of this study was to predict that treatment response. But the secondary aim was to sort of figure out whether or not these inflammatory cytokines contributed in any way to being able to predict that outcome. And so going back to, we want to be able to build a good prediction model, but we also want to know something about how well or how important those particular cytokines are in predicting that outcome. Okay, so we're going to launch now into all of the different methods, and we're going to start with artificial neural networks. So artificial neural networks themselves are modeled after the brain, and the only reason I point this out is because the features and the outputs are often referred to as neurons. So just throwing that out there. But the typical neural network itself consists of the list of things shown here. So we have our set of observed input features, which would be sort of our predictors. So that last slide that I was on with the lupus nephritis, that's the clinical predictors, the demographic variables, the inflammatory cytokines. We then have a set of derived features. So for anybody in the group that does latent class modeling, we can think about these as latent variables that we're trying to derive based on our input features. And then we have our outcomes that we want to explain or predict. And in this case, for our example, it's the treatment response, yes, no, but we can imagine sort of any either categorical or continuous response that we wanted to make a prediction on. And then lastly, sort of allowing us to move between our input features, our derived features, and our outcome, we have weights that are connecting our inputs, our derived features, and our outputs. And the simplest type, and the one that we're going to focus on, is something referred to as a feed-forward artificial neural network, which means information feeds forward through the network to make a prediction on the outcome and not back the other direction. So just to give a generic example, they can be represented as graphical models. So just starting off from the idea of being able to visually show a collaborator what the model looks like, you can actually show a picture of the neural network that you've come up with. But as you can see here, so in this general case, we have these features 1 through P, we have this derived layer, derived layer here, Z1 through ZM, and our outputs Y1 through YK. And you can see there's connections going from X1 to all of our Z's, X2 to all of our Z's, and then from our Z's to each of our Y's. And so although I can show this to a collaborator, it doesn't really give them a clear picture of what's going on. They just see that everything is connected. So still we have to try to figure out how we're going to elucidate this. So thinking about, so of course, going back one slide. So we have this set of things, our input features, our derived features, and our outputs. So we know what our inputs are, we know what our outputs are. We have a question of how do we get from X to Z and from Z to Y. Okay, so in terms of Z, again, these can be thought of as latent features, and we derive these from our X's by applying an activation function to some weighted linear combination of our original input features. So we take our X's and we build essentially a linear combination of our X's with some weight alpha, and we apply some sort of an activation function. And all I mean by an activation function is let's say that this were linear, we would be applying the identity link. So you can think of this as simply a link function. Depending on what we're trying to do, there are common choices of activation functions. I will say it is pretty rare to use a linear link here. Typically, we're using either the sigmoid or the radial basis functions. So I didn't show them. I'm trying to keep this math as small as possible just because otherwise we've got to explain everything. But I think y'all are somewhat familiar with the sigmoid function. It looks a lot like a logit link. Radial basis function is based on the Gaussian distribution. A sign function would just be sort of an on-off switch, as it were. And that was sort of one of the ones that was implemented early in neural networks, but is fairly less common now. Like I said, usually we use the sigmoid or the radial basis function. So again, we apply this sigmoid or radial basis function to our linear combination, and we use that to calculate our derived features Z1 through Zm. Okay, so once we've got those, right, then we want to predict our outcomes Y, and so we do a similar kind of thing. Now we're going to have a linear combination of our Z's, which I'm defining here as TK, so we have our beta 0K, beta transpose KZ, where again, beta is the weight on our derived features in terms of predicting our outcomes Y. We apply another link function here to get a predicted outcome, and it sort of depends on what we want to do at this point. If we're talking about a classification model, so Y is a class variable, we're typically going to be applying the softmax function shown here. And that, going back to our prior slide in terms of how we derived our Z, if we use the sigmoid function to derive Z, we're often using the softmax to get our predicted outputs. And if we're talking about a regression neural network, we just use the identity link function. Okay, so we can see that we can get between these different layers. But the question is, how do we go about doing that? So just a little bit on that. There are a lot of ways that you can go about this. Sort of one of the earlier approaches, and I would say pretty commonly implemented approaches, is to use backpropagation to learn those parameters or weights in a feed-forward neural network. So remember, feed-forward neural network, we're going from the inputs to the hidden layer to the outputs, and there's no back information flowing back the other direction. But in terms of estimating those weights, we do use a backpropagation algorithm. And so we're provided with these inputs and outputs, and we want to calculate our estimated outputs. Then we backpropagate calculated error, and we repeat that process iteratively. So the iteration comes in that we apply a stochastic gradient descent algorithm. So as we're backpropagating and calculating that error, we're using derivatives of the weights. And so you're essentially moving in the direction of steepest descent for those partial derivatives for each of the weights as we move back in our neural network. So going from Y to Z, Z to X. There's only, this is probably more information that you'll actually need, but it ties into one of the weights that I'm going to talk about. Okay, so if we think about a simple example, so that first example I showed was relatively complicated, but we have a simple example here. We only have 4 input features, so we have 4 predictors that we're interested in. We decide to go with 3 hidden features in our hidden layer. So we have Z1, Z2, Z3, and our Y1 and Y2. Okay, so again, we could show graphically. The model itself will return our alpha 1, 1, alpha 1, 2, alpha 1, 3. So it'll return all of these weights. It'll return all of these weights. So we could draw this picture for a collaborator, and it would give them a visual of what the model actually looked like. But from that, it'd be really hard to gauge what the relative importance of the different input features X1 through X4 was. So in looking at this, we can start to think about, okay, well, what if I place emphasis just, I'm interested in X1. Well, so clearly the things that tell me something about the relationship between X1 and my outputs would be the weights that go from X1 all the way to Y. So here I've highlighted, we have alpha 1, alpha 1, 1, alpha 1, 2, alpha 1, 3 going to our Z1, Z2, Z3. And then from Z1, Z2, Z3, we have all of our betas going into our Y1 and Y2 respectively. We could certainly imagine that the magnitude of those weights would have something to do with how important X1 is in determining what Y is. And that is the basis for a large class of variable importance measures that have been developed for artificial neural networks. And the focus of what I'm going to talk about. Now, we're going to go through these, and then I'll mention there are some other ways that you can go about this, but a lot of the importance measures developed for artificial neural networks, again, are based on those relative weights that you see for the neural network. So the first approach that was developed in 1995 by Garçon, and I think in 91, and then in 95 it was Go sort of advanced it a little bit further. And essentially what they proposed to do was, you look at, going back to our picture, right? So for X1, we have a set of weights that's specific to X1. So we're summing the absolute value of the product of the weights going from X to Z, which is that alpha LM, and from Z to Y, which is our beta MK. And that's just for predictor L. And then we're summing across all of our hidden layers and then across all of our predictors, all of the weights. So essentially looking at how much, what is the weight, total weight for predictor L relative to all of the weights that we observe. And then the relative importance is just that SL that we calculate here divided by the total sum of all of our SLs or SJs and multiplied by 100. So essentially you're getting the percent of how much influence it has on your outcome Y. So that was the first one that was developed. In 2002, there was a group that came along and thought, well, you know, actually we feel like the direction of the weight. So if I think about these alphas and these betas, they can be positive or negative. I mean, they look a lot like things we've seen for linear and logistic regression, and essentially they are. It's a weighted linear combination. And they thought that perhaps the weights, the direction of the weights had importance in terms of determining how important a variable was in predicting an outcome, and they felt like that was lost in the Garson's approach. And so they proposed an alternative called connection weights, in which they're just simply summing across my M hidden layers, my alpha L M times my beta MK without taking the absolute value. So you can imagine that if I have for X1, some weights that are positive and some weights that are negative, I might end up with a connection weight that's close to 0. We could also end up with negative connection weights, and we'll talk about that when we look at these for our lupus nephritis example. And then more recently, in like 2013, Abraham et al. Proposed the most squares method, which is now, so what you'll notice about this particular approach, like in Garson's and in connection weights, we have the beta MK, which is the weight going from the hidden layer Z to our output Y. They're only focused on the input weights going from X to Z, and they don't really care what happens going from Z to Y. But what they are looking at, this little I and this little F, superscript for our alphas, they look at the weight that's initialized when you start building your neural network relative to the final weight that you get once you've finished your back propagation algorithm. The argument being is the bigger the change you see from that initial weight that you guessed at to the final weight that you obtained, the more important it is. So if I see a big change, it must be an important variable. If I see a small change, not very important. So 2 of these 3 approaches are available in R. And then all of this is done in R. So we have the Garson's and the connection weights are both available in R. Most squares you can calculate relatively easily from the neural nets package. So when we look at these weights, right, so it does just give a relative importance in the case of Garson's and most squares. So in Garson's and most squares, they sum to either 1 or 100, depending on whether or not you decided to multiply by 100. In these cases, this is just summing to 1, this is summing to 1. So this is thinking about, this is like the percent of contribution to predicting your outcome. And in terms of the connection weights, as I pointed out on the prior slide, they felt like you needed to account for the magnitude and direction of the weights. And so you get weights that don't sum to 1 and clearly vary from something positive to something negative. The other thing that you'll notice is in applying these 3 different approaches that are all based on the connection weights, the rankings of the variables are somewhat different. So for Garson's, what we see is IL-2RA, which is interleukin 2 receptor alpha, if you really want to know, is the most highly ranked variable, and that's true for the connection weights as well. Garson's, we then have urine protein to creatinine ratio, but that's a very strong negative weight in connection weight. Now, in connection weights, they really do just rank them like this is the most important because it's the most positive, this is the least important because it's very negative. It's not clear to me from the literature that that's holds true. I mean, if we thought about this from the standpoint of if we were just looking at a regression model, that a negative coefficient, the magnitude, if that negative coefficient was really, really big, it's still important in predicting our outcome. So there's a little bit of controversy about using the connection weights the way that they were originally proposed. The most square weights, again, shown here, vary from, we have IL-8 as being our most important, which if we look on Garson's and on connection weights, they don't really map together. They don't match one another all that well. So there is actually often a lot of disparity between the weights that you use. And we'll talk about that as we continue to move forward. But needless to say, you get these kind of plots. And you could show this to an investigator and they can very clearly see, depending on which one you picked, oh, well, okay, so IL-2R alpha is, way more important than, say, race. Okay, well, that's good to know, and they're happy with that and helps them feel a little bit more comfortable with the model. Now, none of this addresses the idea of what is the actual impact of each individual predictor on our outcome. So if we think about linear regression or logistic regression, we can say something about the magnitude of that relationship and the impact. If I change that variable X, what happens to Y? We do sort of lose this in machine learning approaches, but in neural networks, they developed something called a Lek profile plot, which allows us to examine the impact of a particular feature XJ on our outcome Y. So here we're showing all of our variables across the top. And then we have a predicted probability of response is our y-axis. And so what you're seeing is these groups 1, 2, 3 are simply so the way that Lek plots work, you fix all other covariates. So if I'm looking at age, I fix everything else at a particular quantile. So the median observed in the data for all the rest of the variables, or the mean, or whatever you want it to be. And then I allow age to vary so I can understand what happens on age, conditioning on everything else staying the same. In this case, the 1, 2, and 3, this is the 25th, the 50th, and the 75th percentile. So when I'm looking at age, I'm fixing everything else at either the 25th, the 50th, or the 75th percentile, and then varying age. And same thing as I move across. What you'll note is, for the most part, you can kind of see the relationship doesn't really change as I shift the quantiles, but for some of them like IL-8, I can see here that the relationship at the 25th percentile looks a little bit different than the relationship at the 50th and the 70th. So it is dependent on where you fix the other points, which is not true for regression. So the caveat with these plots is to use them with a little caution and make sure that you help a collaborator understand what they actually mean. Okay, so there are a couple caveats. There are lots of importance measures that have been developed for artificial neural networks. So I presented 3, and then the Lek plot. So there are more weight-based importance measures that do things like accounting for the variance as you estimate the alphas and the betas, so those weights going back and forth. So they believe that the higher the variability in estimating those weights, the more important that they are. There are some that account for the correlation between the outcome and the predictor of interest, adjusting for everything else. There's another set of weights that's based on the partial derivative of the weights from the output with respect to the input, and then we can use variable selection. So there's lots of different approaches that have been proposed. The issue with that is in head-to-head comparisons of all these different approaches that I'm showing here, there's no one clear winner. So I've seen papers that report that the connection weights are the best. I've seen ones that report that the partial derivative is the best. I've seen ones that report that this most squares is the best. So it's not clear. It's not necessarily clear. So providing guidance on that is a little bit tough. The other thing I would say is, in recent years, particularly with the advancement of computing, we've developed things like deep neural networks and convolutional neural networks, and they're becoming much more popular and can be better performers than sort of the single hidden layer neural networks that we've been talking about. And these approaches were mostly developed for the single hidden layer feed-forward networks. So not that they aren't being extended to these deep networks and the convolutional neural networks, but they're not there yet. And then I already talked about the last issue with the Lek profiles. Okay, so that's all about ANDs. Now we can talk about tree-based methods. So for anybody that's not familiar, they're non-parametric or semi-parametric methods. And the really nice thing about them, to a degree, is that the models can be represented graphically. So clinicians and collaborators tend to find these very intuitive relative to almost every other machine learning model that's out there. And from a standpoint of use in medicine, the way that decision trees operate is very similar to think about making decisions about patient care. And so they're really comfortable with them. There are lots of them out there. I show a list of some of them here. So classification regression trees, or CART, was one of the first methods, and there have been extensions of that since. And we also have C45, C5, Quest, Cruise, and there are other ones, Guide, etc. So there's a lot of versions. We're going to focus on CART because it was one of the first ones developed. But a lot of these approaches can be applied to these other decision tree approaches. So Main idea in classification regression trees, or CART, which is we're going to call it from now on, is to divide our feature space into disjoint regions and then fit simple models to each of those regions. So for classification, we can imagine as we divide our space into these disjoint regions, we're just using the most frequent class in each region to predict what the class happens to be. In regression, we would think about the mean in that region. And so we can fit a simple linear model to that region, or a simple logistic model to that region, or just a simple classifier to that region to get a classification out of a CART tree, or a regression mean out of a CART tree. So to look at an example, as I said, they can be represented graphically. So we have a picture here. We have feature space that consists of two features, x1 and x2, and data points that are either of the red class or of the blue class. So we can see that using our CART tree, we divided it into disjoint regions. So we have the region defined by x2 being less than -1, which is under the green line here, and you're blue if you're in that region, because only blue points are in that region. Then we divided on the purple so that we now have a region that's divided by the green and the purple, which is all red. So this guy here and everybody else, and so on and so forth. So you can kind of see how it's dividing, simply basically using single splits in the data to divide this space into simple regions so that you can classify. Within the tree, the binary splits that we're looking at are what are referred to as nodes. The branches lead down from the splits, and terminal nodes are anywhere where we're making a prediction. So these things down here that say blue or red are terminal nodes. Tree itself is fit using recursive partitioning, or the greedy search. So imagine again, 2 features is not that much, but if we take our lupus nephritis data, it has 10 features. So we consider all possible splits for every feature in our data set, and we picked the predictor and the split that give us the best goodness of fit, improvement in goodness of fit. So if it's a regression tree, we're looking at like mean square error. If it's a classification tree, we're looking at measures of purity. So accuracy, Gini index, deviance, those kinds of things. Once we've done all that, we're going to pick the predictor that has the best split. That's going to divide the data into 2 subsets, as you saw on the prior slide. And then we do that with each subset that we develop as we go through the tree. So you're now once you've made a split, you're only looking at the subset that meets the criteria of that split, and then you split again. And again, you're going to repeat that process essentially until you reach some terminal node. So first line of defense in CART for variable importance is just looking at the decision tree. Relatively interpretable. Not all variables that you include in the data are going to be included in the tree, and the higher up there, higher they are in the tree, the more important they are likely to be. So at least that would be one argument you could use. But there is a formal measure of variable importance that's developed for CART that does the relative ranking like we just saw with the neural nets. And it's going to be based on this idea of sort of increase in purity each time a variable is used to make a split. So like if we go back to our tree here, when I make this split on x2, I would look at how pure this is and how pure this is, and how much increase in purity did I gain by making that split. And then every time x2 appears, I would calculate that. But it considers an additional piece. So as a CART tree is being built, it does something called a surrogate split. And the surrogate split was originally developed to address the idea of if I'm applying new data and I split on xj in my tree and I'm missing xj in my data, surrogate split would pick another predictor that was similar to xj in terms of its ability to discriminate, and it would use that predictor instead to decide which branch I should go down. And again, doing the same approach, so it's still applying that recursive partitioning to pick the best surrogate split for variable xj when I split on xj at c. But for each node in a tree, I can have up to 5 surrogate splits that are stored by CART. And so when we do the variable importance, we're not only summing where I see xj in the tree, I'm also summing where it's a surrogate. But for the sum when it's a surrogate, I'm adjusting by the goodness of fit. So if I picked xj for a split, I picked it for a reason. It gave me the best separation of the data at that point. If I pick surrogate xk for variable xj, I look at the level of agreement between xk and xj, and that tells me how well xk mimics xj, and then I can adjust that by how well xj predicted. And so that's sort of how that's incorporated. Now, what this does is it allows you to get importance for variables that aren't included in the tree. So looking at our example in lupus nephritis, of course, our first line of defense, we have a tree. So here's our tree that we built. We start by splitting on IL-2 or alpha, Going down the left branch, we split on urine protein to creatinine, then on eGFR, then on age several times, then on IL-8, then on IL-12, and we get predictions at the bottom. Going to the right branch, we split just on eGFR. This tree was developed in something called the party package, which, by the way, produces much prettier trees than the other tree functions and CART functions in R. It tells you what proportion of the observations were included in that set, what proportion voted for being a 1, and what the class prediction is. So the class is 0, 12% of the observations in this node were 1s, and 52% of the data are in this node. So you kind of get a feel for how you would read that tree. Now, in this tree, we only include IL2RA, URPR, CR, EGFR, age, IL8, and IL12. So we include 6 of the 10 variables. If we look at the variable importance we get out of CART, it reports 9 of the 10 variables. So this goes back to that idea that it's counting both. As long as you're in at least one surrogate split, CART is going to calculate an importance measure for you. So you may not appear in the tree, but if you were a surrogate split for somebody else, you get counted as part of the variable importance. And so, for example, race, I'm trying to get my mouse to show up. There we are. Race and C4 don't appear anywhere in the tree, but they're both included in the importance measure. Now, with relatively low importance, but they are included. Okay, so there are a lot of caveats with CART trees. CART models themselves are super intuitive and easy for non-statisticians and non-data scientists to understand. The danger is they are what's known as a weak learner. So very small changes in the data can yield a very different model, which means that they don't generalize well. So if you're trying to use them to make predictions, they'll often predict very well on the data set you use to build them. And then when you go to predict anything else, they're terrible. So that's the main caveat. So what can we do about that? Well, ensembles, for those of you that are familiar with them, were developed in part to fix the problem of a weak learner. So one of the most notable improvements that we observed with CART came with the advent of ensemble learners. So in an ensemble learner, we build a whole bunch of weak learners, in this case, CART models, and we use that whole group of weak learners that we've developed to make a prediction. So if we think about a typical ensemble has anywhere from 100 to 1,000, say, CART trees. So each tree is allowed to predict what class or what mean response we have, and then we average that across the class, across the different trees. And by doing that aggregation, we in theory end up with something that's no longer a weak learner. So it addresses the issues that we have with CART. There are lots of different approaches, well, three different approaches that have been proposed for building ensemble models. So they're all shown here. Boosting so we're going to talk about AdaBoost and random forest. And so we need to understand all of these in order to do that. So boosting, what we do is we sequentially apply this weak learning algorithm, so CART, to modified versions of our training data to yield a weighted set of classifiers. That sounds like a lot of words, and I know I just read it off the slide. We'll talk about what that means in a minute. In the case of bagging, bagging means bootstrap aggregating. So we're going to draw bootstrap samples from the data and apply weak classifying algorithms to each of our bootstrap samples so that we get a collection of classifiers. And the final one, which is very rarely used by itself, is randomization. And so in randomization, what we'll do is we select a subset of the predictors or features from our data and construct our weak classifier on that subset to, again, yield a collection of weak classifiers. So imagine that you keep sampling from the subset of predictors and you build classifiers off those subsets. Okay, so the main boosting algorithm, and there's several boosting algorithms out there, but the main boosting algorithm that sort of kicked off the idea of a boosted ensemble was AdaBoost. So I'm showing, and I know it's a lot of math, but I'm showing the AdaBoost algorithm here. So we start by initializing our observation weights. So we're going to weight our observations and we're going to weight our trees. At the beginning, we initialize our observation weights such that each observation has equal weight. Then we're going to run through a total of capital M iterations. So at iteration 1, or iteration little m, we're going to fit a classifier gm of x, which is we can think of as a CART tree, using these weights, these observation-specific weights, wi. Then we're going to calculate a weighted error for that classifier that we've just built. So in the case of a classifier, this is an indicator if yi is not equal to our classifier gm of x. So gm of x makes a prediction. If it doesn't equal yi, then that takes value 1, and I give that some weight, and I divide by the total sum of the weights. So I get a weighted error rate. Then I'm going to use a model-specific weight, or I'm going to calculate a model-specific weight, alpha m, by taking the log of 1 minus the error divided by the error. And then I'm going to update my observation weight. So essentially what we're trying to do is we're trying to, at each iteration, update those observations, give more weight to those observations which were poorly predicted in the prior model. So the idea being, imagine if we had a heterogeneous population and some subset was particularly hard to predict, you would keep upweighting them until you found a classifier that could predict those observations very well. The final ensemble then is just given by the sum of our weighted classifiers. So alpha m again being that weight specific to the classifier. So though we use the observation specific weights in finding our models, they're not used in terms of making a prediction. Now, clearly, we went from the single tree, which was really easy to understand, to now having an ensemble of trees, and we'd like to be able to say something about the ensemble of trees and the importance of the variables going into it. So the original authors of AdaBoost proposed a squared importance measure. So we start by thinking about the mth tree in particular. So we have model GM, which again is our CART model for the mth iteration of our AdaBoost algorithm. The squared variable importance then is just this measure shown here, where L is the number of internal nodes. So that's sort of all the nodes that aren't terminal nodes in our CART tree at that particular iteration, times d hat of k, which is the improvement in misclassification by making our kth split. So, right, we imagine xj was split at k different nodes, and so we're looking at how well that split improves the overall fit. So very similar to what we did with CART. But now I've got a whole bunch of trees that I can apply this to, so I can take that squared importance and average it across all of my trees to get an importance measure for each feature xj. Now, as I said, when you do ensembles, you tend to lose a little bit of the pleasure of showing people CART trees that make them really happy because they understand what they mean. You can extract the individual trees from a boosted model. So this is in particular for the lupus nephritis example, I'm showing you the first and I think the 25th tree out of 100 trees. And you can plot them so they can kind of get it. So you could show them, look, here's an example of 2 trees out of the algorithm. And you can see that they include somewhat different variables. So the first tree, we're involving urine protein to creatinine, IL-2RA, IL-8, EGFR, and age. The second tree, or tree 25, includes just EGFR, IL-2RA, and C4. But I think the relative importance measure is even more useful, kind of like what we talked about with both of the preceding methods, and that you get a ranking of the variables relative to one another in terms of how well they predict the outcome. So similar plot to everything else we've seen, still relative. In this case, these sum to be 100. So you'll notice the highest one is, I think, 16. The lowest one is probably 2 or 3, 2. So 2 to 16. So it kind of gives you an idea of who's most influential in terms of this boosting model. You'll also, if you were paying attention, notice the ordering is very different for boosting. Okay, so the other popular approach that I'm pretty sure everybody's heard of is random forest. So random forest takes 2 approaches. It considers the bagging, which is that bootstrap aggregating. So we're going to do bootstrap sampling to build the random forest, but it also incorporates randomization. So number one, it's better than it usually does better than a single CART model. It's also more computationally efficient relative to boosting or bagging. And this is because not only do we select by selecting a random subset of predictors, we're having to sort of sort through less predictors on which to make our split. The last point that I would make is it generates something called an out-of-bag data set, which turns out to be very useful for the purposes of what we're talking about, this idea of variable importance. So, right, if I'm drawing a bootstrap sample of size n, I pick about 62.3% of the data at each iteration of that bootstrapping, and therefore about 37% is left out. That 37% that's left out at that iteration is the out-of-bag data for that particular tree. So, going through the random forest algorithm, we have our data, which has response vector y and a set of features x. In this case, we're going to have b trees. So we're going through iterations b equals 1 to b. We're going to draw a bootstrap sample from our data, as I mentioned, of size n. So we'll have sample WB, and then we'll have that out-of-bag data that's left out. So that 37 or so percent that isn't included in our bootstrap sample. We fit our CART tree to that bootstrap sample, but we take an additional step. So in fitting a CART tree, we consider all of the predictors at each split to pick the best predictor and the best split. In the case of random forests, at each split within a tree, we pick a random subset of those predictors. So that's the randomization component, and we split only on that random subset. We get 2 new subsets of data, we pick 2 new splits, but the same thing for each of those subsets, we select an entirely new subset of predictors on which to make our split. Once we do that, then we grow the cart tree to perfect fit. And so we end up with this forest of B trees. And again, just like with the, so in the case of the AdaBoost model, we had a weighted indicator that, weighted indicator of majority class. This is a non-weighted indicator of majority class. So I said the out-of-bag data was important. So there's a couple things that we can do with it. So like I said, that out-of-bag data for the Beeth tree, so tree GB, was not used in building the tree. So we can think about that as being test data for the Beeth tree, which means that we can calculate an error rate using that data and treat it as if it were test data. So it's sort of a way to do validation of that tree and how well it predicts on data that wasn't used to construct it. And so it's a much more unbiased estimate of the error for that particular tree, right? So then we can imagine, and for each observation itself, it's in about 1/3 of the out-of-bag data set. So for each tree in the forest for which observation I was left out, that tree can make a prediction on those data, and I can get an average prediction for observation I across all of my out-of-bag data sets. And I can do that for all observations to get an overall out-of-bag error rate. The reason this is important is it's interesting to have that measure of how well the model fits this unbiased estimate of error, which is important if we're trying to understand how well our model predicts. But it also allows us to do our variable importance measure. So the way that the original variable importance measure in random forest was developed, we start by estimating that out-of-bag error. What we're then going to do is take our original data and we're going to take the column that represents predictor xj and we're going to permute it. So the idea being we disrupt the relationship between predictor xj and outcome y. We're then going to make new predictions with xj permuted and get a permuted out-of-bag error rate. And we take the difference between the out-of-bag error rate with permutation and without permutation. The assumption being if xj is important in making a prediction on y, when I disrupt that relationship, I should get worse error. So they're not quite as pretty. This is the default plot that you get out of the random forest in R. You could make them look like the lovely bar plots that I showed for everything else if you really wanted to using ggplots, but I just returned the default one. So I made the comment earlier that it was originally based on the out-of-bag error rate, which has to do with accuracy. It's since been also developed where you were looking rather than accuracy as your measure of purity, using Gini index as your measure of purity. And so random forest by default, when you ask it to return importance plots, will generally give you both. So that's what you're seeing here. This is based on the mean decrease in accuracy, and this is based on the mean decrease in the Gini as we permute age, IL2RA, EGFR, URPRC, or so on and so forth. What you will notice is they tend to give you slightly different answers, and there is some literature that points to the mean decrease in accuracy being a better indicator of importance. So I tend to use this one, but I have found literature in the other direction as well. I felt like the paper was stronger that showed mean decrease in accuracy was better. So just to be aware, you've got these two, mean decrease in accuracy there's some evidence that it's a little bit better measure and that the ordering that it gives is a little more appropriate. Now, random forest also has a bunch of other features. So you can get something called a proximity measure out of random forest. So imagine this is sort of measuring the similarity between observation I and observation J. So we're potentially dealing with very high dimensional data. It's really hard to know why, subject 1 and subject 2, it's hard to see that subject 1 and subject 2 are very similar. So what the proximity does is for each pair of out-of-bag observations that share a terminal node, it increases the proximity of 1. So if I'm making a prediction on observation I and observation J, they're both in the same out-of-bag data set and they end up in the same terminal node, my proximity goes up by 1. I evaluate that across all of the trees in the forest, yielding an n by n proximity matrix for each pair of observations to give me an idea of similarity. What I will say is this is useful to us as statisticians and data scientists. It's not super useful to a clinician or a collaborator. At least I don't find it so. But what we would typically use it for is something like trying to identify outliers. So if we think about regression techniques, we have all of these approaches to allow us to evaluate how well the model's fitting, less so with machine learning approaches. And so the proximity approach gives us a way to, number one, take the data from high dimension and display it in low dimension. So here I'm doing a multidimensional scaling plot, which is essentially putting our data in 2 dimensions. And we could then see if there are any outliers. This would also give us an idea of like, okay, there is some level of class separation. We could do principal components analysis on this. So it does provide some means of visualization and doing a little bit of model checking. Now, again, there are caveats with some of these. So they are both useful for improving these weak learners. In terms of random forest, there's been a lot of extensions of the importance measures that have been developed. Number one, because notably people have observed bias in those measures. Bias with respect to, firstly, that they're more likely to give more weight and more emphasis and more importance to variables that are continuous as opposed to variables that are categorical. So if I have a data set that has sex or has ethnicity in it, and I have then all these other continuous measures, sex and ethnicity may end up being ranked very low, not because they're not important, because they're categorical. Also, there have been some folks trying to address the idea of if I have collinear predictors, essentially, if my predictors are highly correlated, we can see bias in random forest as well in terms of their importance measures. And so there have been some fixes proposed for that. I will say there's been less evaluation of the importance measures out of Boost. So they do tend to be the most different in terms of the ranking that they give back relative to everybody else, and we'll see that. Okay, last one. So this one, guys, I'm telling you, support vector machines, it's hard to talk about these in short order, so we'll do the best we can. And they're also the ones with the least ability to show you some kind of good variable importance. So we'll start with that caveat.
And Beth, I just wanted to let you know we have about 10 minutes left.
Okay, guys, it's going to be fun. Okay, so the general idea is it's generalization of a linear decision boundary. So if I thought about, if I have an outcome y and a predictor x, and I can define a line that, and x and y is a class variable, and I can define a line that basically all the y's that are ones are on one side and all the y's that are 0 are on one side, then that's a linear decision boundary. We want to be able to generalize that. And so support vector machines were really developed to be able to provide the idea of a more generalized hyperplane. The really nice feature about these things is because of the way that they operate. So they use they optimize a convex loss function with respect to binary outcome. And as a result, it tends to be that they're scalable to multidimensional data. In fact, they often can scale to very high dimensions. And they tend to be unaffected by local minima. So there are, assuming that you tune them well, they can actually be very good prediction models, but they're also, of the methods, the most black box. So there are a couple of basic components of an SVM that we need to think about how we would develop. The first is the separating hyperplane, which we've just talked about. So the idea of some decision boundary that defines our two classes. So on one side of the line, you're one class, on the other side of the line, you're a different class. We also then have things called the maximum margin of the hyperplane, the soft margin, and the kernel function. So the maximum margin of the hyperplane, if we thought about drawing a line to try to separate two classes, the margin then is how far is the closest point from each of those classes to that line separating the two classes. That distance gives us the idea of the maximum margin. Now, a maximum margin assumes that all of the points from each class fall on the appropriate side of the line. Most of the time that's not true, and if it happens to be true, we probably overfit. And so the soft margin allows us to relax that assumption that the points are all on the appropriate side of the line, and allows some points of the wrong class to go on the opposite side of the line, but penalizes based on where they are relative to where the line is. And then the kernel function, we'll see, allows us to get at this idea of nonlinear decision boundaries in our original feature space. So if we start by thinking about the idea of linearly separable data, we can see we have this function here, f of x is equal to beta naught plus x transpose beta. So it looks like a linear regression model. And we're setting that equal to 0. So that gives us our line. So where this is true is where our linear decision boundary occurs. That's the hyperplane that we're defining. We then want to choose the best hyperplane by defining two distances, d minus and d plus, that are our shortest distance from the nearest negative data point and positive data point. And when I say negative and positive, the reason is in support vector machines, we typically define classes as +1 and -1 and not 0 and 1, so that that difference comes to 0. And we can see then that in terms of that idea of the optimal margin, our margin is then just a total of the distance between D- and D+. So as we've said, that's the hyperplane that then runs through the middle of that margin, D1, D plus to D-. And we modeled the parameters that define that margin by a convex optimization problem. So we use a local solution to find a global optimum. And the end, of course, is a hyperplane that's dominated by points that are near that margin, either near or on. So it turns out that the margin is defined by the points that are at D- and D+ on either side of the line, and those are what are referred to as support vectors. So just from a picture standpoint, here I've got my red class and my blue class. So these points that are circled would be the support vectors defining that hyperplane. Main problem with the hyperplane. So just to give you an example here, so I've got my green points and I've got my red points. And I can see that there are a whole bunch of hyperplanes that I could define that would separate those data equally well. So in the case of all these lines that are drawn, everybody's green class on one side and everybody's red class on the other side. So we have to think about how we're going to pick the best one. I don't need that, so we're going to skip that. We also want to be able to generalize this to a nonlinear case. So everything that I've shown so far is the idea of a linear case. And we also want to be able to separate in the case that we're not, be able to deal with the case where we're not perfectly linearly separable. So support vector machines generalize this by, number one, allowing features, hyperplanes that are not linear in our original features X, and the data don't have to be perfectly separated. So let's start with the idea of the linearly non-separable data. So again, in reality, if we truly are able to separate the data perfectly, we probably overfit the model. And so support vector machines introduce something called a soft margin, which I mentioned this earlier. So that allows points to fall within the margin and then often on the wrong side of the margin. So it's allowing for misclassification. The distance from the point on the wrong side of D+ or D- is what's referred to as a slack variable. And the slack variable is defined, that sort of tells you how much weight you want to give that observation. So the further it is from being correct, the less emphasis you want it to have in terms of defining the hyperplane. So a little more on the soft margin. As I said, it's going to penalize crossover. So we have a picture here. We have our y-1 and y1. We can see that we have some variables that fall exactly on our boundary at D+ and D-. And then we have some that fall on the wrong side. And we see now that we have a slack variable that's less than 1 or greater than 1, depending on where we are, and a slack variable that's 0 for anything that's either on the margin or outside of the margin. So of course, the further we are from the soft margin, the less influence we have on prediction. Like I said, support vector machines are tough. Okay, so the other thing we said is linear separation isn't necessarily appropriate in all cases. And so we could think about nonlinear transformations. We do this all the time in statistics, right? So we consider log transformations, squares, polynomials of all sorts. So that's simply applying that same idea here to allow us to take what was originally a linear feature space and project into some higher dimensional space so that we're no longer necessarily linear in our original feature space. And we do this by applying something called a kernel function. So the kernel function is basically going to take our original data and project it into higher dimensions by using transformations to allow separation. Just to give a quick example of why that might work. If we had a single feature X and our outcome Y is the red and green dots, so we have two classes, clearly there's a separation between our red and green classes that we could, and it has something to do with X, but if we look at just the continuum of X, we don't see it. However, if we project X into a higher dimension, so if we square X, we can now draw a line that separates the green class from the red class perfectly well. So support vector machines operate off of this idea that there is some higher dimensional space that I can project into that will give me linear separation. So in that high dimensional space, I will have a linear decision boundary, but I'm going to project it back down into my lower dimensional space to look at. Okay, so to tie all of this together, and it took us a while to get here, but there's a lot of things you do. So in order to find A, the optimal separating hyperplane, B, the appropriate kernel, C, where the support vectors are, we're just going to think from the standpoint of the linear support vector machine. So we want to consider linearly separable data where we have beta naught plus x transpose beta is greater than or equal to +1 versus less than or equal to -1 if y is +1 or -1. And so we have these inequalities. And our goal is then to find the optimal hyperplane that gives us beta naught and beta naught that will give us the best separation of y +1 and y -1. We do this using a convex dual optimization problem where our goal is to minimize the squared norm of beta plus some cost times the sum of our slack variables. So this is allowing us to, again, be misclassified. And we're subjecting that to a constraint where that slack variables all have to be greater than 0, and yi times beta naught plus x transpose beta has to be greater than or equal to 1 minus the slack variable. We do this using Lagrangian multipliers, and I know this is like way above what most of us really want to hear today. It's a lot of talk, but essentially the point is we're again using a convex optimization problem because it's a quadratic objective function, and we use linear inequality constraints, and we apply this in the case of our Lagrange multipliers where we now have this Lagrange multiplier alpha I. And we're going to minimize LP with respect to our primal variables beta and beta naught, and maximize with respect to our dual variables alpha I. This is, if you want to look it up, this is called the dual Wolf problem. You can look up how this is done. But essentially, the whole reason I'm pointing this out is this is how we're going to find our optimal hyperplane. And this alpha I is what's going to define our support vector. So alpha I is only going to take value greater than 0 for those things that either fall on the margin or within the margin, or well, within the margin. And so though we need all of our data to find them, the support vectors that fall on the margin or in the margin, so that subset of observations that are on or in the margin are the only things defining the hyperplane, which is what has made variable importance so difficult in support vector machines. So how do we use any of that information that I just threw at you to try to figure out variable importance? So the only way that's been proposed in literature, or one of the only ways that's been proposed in literature, is to use recursive feature elimination. So we've not talked about feature selection, but it is an alternative approach that you could use. And it's the only one currently available for support vector machines because, of course, we're only having weights on a subset of our original data. And so I think there's some hesitation about how do you go about finding feature importance. So essentially, the way recursive feature elimination works, we fit an SVM with all our features. We calculate our support weight. So again, this is the alpha I times yi times x is the weight for the observations that fall on the hyperplane. Alpha I is that Lagrange multiplier that we estimated, and so on and so forth. And then we're going to, then you take those and you rank them and you remove the feature with the lowest rank, and you basically iterate that process until you have one feature left. And the order in which they were removed gives you an idea of how important they are. So first one removed is the least important, second one removed is the second least important, so on and so forth. There are also some visualization approaches that have been proposed. Firstly, to look at the decision boundary and two-dimensional feature space to help understand how the boundary actually looks when it's projected back down into the normal feature space. And then there's also been a more recent method proposed where we look at the change in xj on y using something called pseudo data. So this is going to look a lot like the Lec plots that we talked about with neural nets. So looking at our recursive feature selection for in our lupus data, again, just going down, it's going to be 15, 14, 13, 12, so on and so forth, because this is the order. IL-8 was removed first, then IL-12, so on and so forth. So it doesn't give you the level of gradation that you see with some of the other feature importance algorithms for neural networks, for CART, for any of the boosting method, for the ensemble methods, but it does at least give you a rank. In terms of visualization, again, we can do something like a Lec plot. So this is now fixing all of the other variables at their median and varying age, urine protein, creatinine, C4, EGFR, so on and so forth, and looking at how the probability of response changes as you change that other variable, holding everything else constant. And again, this is holding everybody constant at the median. We can also, again, project down it. And I apologize, these are the default colors for this particular, I think this is E1071. These are the default colors for you plotting the decision boundary. So what we have is essentially picking two of the features. So this is age and urine protein and creatinine, age and EGFR, urine protein and creatinine and EGFR, so on and so forth. And then they're telling you whether it's class 1 or class 0 is the blue, and the shape of the decision boundary in that two-dimensional space. I personally don't find these to be that helpful, but it is a way to visualize the impact of a particular pair of variables on the outcome. That's been advanced a little bit in an alternative package. So this is coming from the Kern Lab package, and it allows you to, you're plotting it in 2 dimensions. So you're plotting it by 2 of the variables, but then you're allowing a third variable to change. So what I'm doing here is keeping my 2 variables are IL-2, are alpha, and EGFR, and I'm allowing age to vary as I go along, and I can see how the decision boundary changes, and it shows it sort of as a contour plot. So, as I said, these are the most black box of the methods that we've discussed, and probably the hardest ones for collaborators who are uncomfortable with not knowing what the model is actually doing to digest. So the other thing is, unlike ANDS and the decision tree approaches that we discussed, there isn't a good semi-quantitative feature importance measure. I mean, yes, you get an absolute ranking, but it doesn't really kind of tell you the relative quantitative importance of those things. The other thing is, because we're doing feature selection, the rank that we get is conditional on the features that are in the model at that given iteration. So essentially it's a discontinuous process, and for all you know, if you had removed a slightly more important feature earlier on, then your ordering of your feature importance would have been very different. So putting it all together, first thing I would say is we've looked at all these different approaches. When we compare the different approaches using, and this is all applied to that same data set, so all based on the lupus nephritis data set, rankings aren't necessarily consistent. So when you're fitting different models, don't anticipate that you're always going to get the same things coming out as being most important. Consistency does give you some degree of comfort that you're probably closer than not to those that are important. You also have to consider you might be including some noise variables, so spurious predictors. So if I rank them, this is ranked based on their average rank across all the models. So the nice thing in this data, they were really interested in these inflammatory cytokines. So IL-2R alpha actually ranked fairly consistently high, with the exception of AdaBoost, across all of the models. So it was either rank 1 or rank 2 in everything except the AdaBoost model. And as I pointed out when we were talking about AdaBoost, it was the one that was least evaluated in the literature, followed by EGFR. But your rankings, you can see, start to get much more inconsistent as you move down through the list. So EGFR ranked from anywhere from 1 to 5, age anywhere from 1 to 9. So you don't necessarily get a whole lot of consistency. So this kind of leads to the idea of you need to also potentially combine this with feature selection, which we didn't have time to talk about. Another caveat, all of these methods that we talked about require some level of tuning. They all have tuning parameters that you have to consider, and you can do things like grid searches using cross-validation to try to find the best parameters to tune your model to get the most appropriate fit. But failure to do so can lead to very poor fit and poor feature importance. So this is comparing, this was the original Garson's feature ranking from a tuned artificial neural network. This was me picking some things at random. So we see that we had IL-2RA, URPR, CRC4. This one ranks C4 complement highest, EGFR high. I mean, they're just very different. So it is kind of worth making sure that you take time to tune these models. Main take-home points. So a lot of these feature importance informations do capitalize on information that's captured in the model. So that was kind of the point of showing you how the models were developed, to understand where the feature importance measures were coming from. But there are other approaches that could be applied. So in general, you could use recursive feature elimination pretty much on any of the approaches. And there are other variable selection methods that have been developed for the various approaches. So there are penalized regression approaches that have been developed for both neural nets and for support vector machines to reduce the number of variables. The Random Forest has a whole slew of variable selection approaches available for it, and so on and so forth. The LEC type plots that we've discussed. So essentially fixing all of the features at a particular quantile and then varying one of the features to look at how the probability or the mean of the response changes. That in theory could be applied to any of these approaches. Similarly, if you had an independent test data set that you had left out when you were developing the model, you could then use a permutation-based approach to try to get at feature importance with any of these approaches. So some things I'd like to leave you with. So where are we going? The research for these methods is ongoing. I was showing you an example in a very low dimensional setting, but high dimensional data has become a big topic. So when we think about any of the omics that are going on, that and just the mass amounts of data that are out there and available to us, oftentimes we're dealing with cases where the number of features is much, much, much larger than the number of observations. There's also research into things like multicollinearity and addressing that issue because it does have an impact on these variable importance measures as well as feature selection approaches. So again, feature selection is the other approach that I didn't have time to talk about. And oftentimes in these models, it's important to remove sort of those spurious noise predictors because leaving them in will often yield worse prediction. And so research in that area is also very active. Here's the various list of R packages that were considered and used in this talk. So NNet, NeuralNet, RSNNS, and NeuralNet tools were used for ANDs. RPart, Party, and Tree were all used for CART, AdaBag, AdaBag, and Fast AdaBoost are used for boosting. Random Forest, and there's others. Random Forest was the only one I used in this, but there's lots of Random Forest packages. E1071 and kernel will let you fit SVMs, and Carrot is a good way to train any of those models and to do recursive feature selection. So I know that was a lot of information. And I have references on this after this if anybody's really particularly interested in one of the things. But I want to thank you all for attending, and I think Jamie's been cataloging any questions there might have been.
Yeah, thanks, Beth. That was an awesome talk. So to all the attendees, if you have questions, you can either chat them in or put them in the Q&A. Or if you do the raise your hand feature, then I can let you unmute and you can ask your question. But I'll go ahead and get started. This one came in a little while ago. The question is, what are some common approaches for unsupervised learning for either feature selection or variable importance?
So that's a good question. And I didn't talk about that because it's interesting. I would say in the world of unsupervised learning, oddly enough, the big things that you see with those are things like heat maps and hierarchical clustering dendrograms. And for whatever reason, people seem comfortable with those. All the collaborators I've ever worked with, so if we're doing any sort of omics research, and I present data as a heat map with dendrograms to cluster either on one axis or both axes, that actually seems to be something that people don't have an issue with. So they're very happy then kind of trying to identify, okay, well, so if we're talking about genes, for example, gene expression, and we do a dendrogram of gene expression, they show the rank of the genes and they see patterns where like there's a cluster of genes that are underexpressed in diseased and overexpressed in non-diseased or vice versa. And they see that they're very comfortable with that idea. So that's pretty popular. I will be honest, I don't know that I know a lot of approaches for feature selection in unsupervised learning approaches. It's just not an area that I've worked a lot in. Again, the visualization piece I've worked a lot with, and in the scientific community in general, people seem to be relatively, like I said, the most common approaches I've seen are the heat map and then using dendrograms, or one or the two. And that makes people pretty happy and they're relatively comfortable with it because they feel like they can identify patterns in the data themselves then, because they can physically put the data points, like data descriptors, to go with the clustering, and they seem happy with that. So hopefully that answered that question to some degree.
Great. So here's another question about shapely values for explainability and variable importance measures. Any thoughts on those values?
I'm not sure. I don't know that I've heard of a shapely value. So if that person has any clarification on it.
I haven't heard of those either. Okay, here are some more questions. Which of the three weighting methods for ANNs do you most subscribe to?
Oy, that's a tough one. The literature on the different weighting methods for artificial neural networks are really varied in their conclusions. Again, the papers that I've read all conclude that a different approach is the most relevant, and all using Monte Carlo simulations. So they're all trying to elucidate that information. What I would say with the caveat to that is, so Garçons, which is the sort of the earliest one that was developed, is the most commonly used. However, in all of the papers that I've read doing head-to-head comparisons of the neural networks, it is not one of the best performers. The partial derivatives method does seem to actually do relatively well across the different papers. It's one of the harder ones to implement. So essentially what you would need would be you would need a neural net that captured the last iteration, captured and stored the last iteration of the backpropagation algorithm, because that would give you that partial derivative of each of the weights for that last backpropagation that picked the final weights. And that's what would be used in the ranking. That I know of, that is not, it's not that you can't get it in the R packages that I listed, but it's not readily available. So if you're writing your own neural network and you have the ability to capture that last bit of the backpropagation, great. If you're using R packages, it's being calculated somewhere. I just have never tried to figure out how it was stored. So there's no implementation that I've seen of anybody using that wasn't doing a direct comparison and was kind of building their own neural nets that way.
Great. So another question is, are there any approaches to test for the significance of predictors in machine learning?
So the best way that I've seen, going back to the idea of that perturbation, where you're doing some permutation of predictor xj. So the way that people have typically done it in the past is essentially you do, say, and this is generally more done for the model, but you can do it for the individual predictors. You permute the predictor, you do 1,000 data sets with the predictor permuted, and you look at the distribution of variable importance measures under that permutation, and you compare your observed variable importance relative to that, and say, well, actually, they take that you permute the full data set and fit 1,000 forests to it or 1,000 models to it, and you look at the distribution of variable importance, and you're seeing if the variable importance that you observe in your fitted model to the original data are as extreme or more extreme than 95% of those, then 90% of those, and those are metrics that people will report in the literature. So essentially, you're generating an empirical null distribution and comparing your feature importance measures to that null distribution. And that, again, I've seen that in the literature, and people seem to accept that reasonably well. And it makes reasonable sense, because if I permute the predictors, then I'm messing up the relationship between the outcome and the predictors. And so I should get a quote unquote null model, and it should give me back null importance measures.
Okay, so another question is about a way to potentially combine all of the different importance measures or come up with a better measure of importance that would be across different models.
Well, this gets at the idea of what I was talking about with a lot of these approaches are generalizable across models. So certainly the potential for that exists. And I go back to, for any students that are out there listening, this is a very hot area of research, and I'm trying to think if I've seen anywhere where somebody's tried to do that specifically, or if it's more just they've applied the same approach across models and then compared the different models. I can't say that I've seen anybody do it. You'd have to think about how do you pool the information, because again, the way that each of these is extracting the variable importance that it's extracting is relative to how the model was built. So I don't have a great answer to that, but I mean, I go back to, there are methods that would generalize to all of these approaches that you could apply to give you at least an idea of how they were doing across methods. Now, combining across methods, there is, and this is kind of off topic, but from a standpoint of combining across models, there is supporting evidence in the literature that combining predictions, not only from like an ensemble type approach, but from an ensemble of different models will often yield a better prediction. So there's some recent literature looking at that idea, at taking multiple prediction models, prediction modeling approaches, applying all of them, and using the aggregate prediction across the different approaches to make a prediction. The idea being, again, they all predict better in certain ways than others and fail in certain ways relative to one another.
Okay, so this is kind of a question related to the previous one, but there's a question about causal interpretations and with decision trees or other machine learning methods?
You know, I mean, so you have to be somewhat hesitant about defining causal relationships, even in traditional statistical approaches, right? So in traditional statistical approaches, we want to have sufficient sort of repeated evidence that there's a relationship that exists to identify causality. Given the obscurity of the relationship in machine learning models relative to between the outcome and the predictors, I'd be hard pressed to say that I would infer causality from a machine learning model. Decision trees in particular, we talked about the issue with those. They really do tend to fit the data that was used to build them very, very well and not generalize well. And so from a causality standpoint, now that being said, there are, I will say with the decision trees and the ensembles, well, actually all of these approaches, there are Bayesian adaptations where you could pull in prior information. So if you had a clinician or a collaborator who had good prior knowledge about sort of the relationship between things, that information could be pulled in, and then you might do a better job of getting at causality, but I still would be hesitant because it's so hard to truly visualize what that relationship is.
So here's another question about how do you isolate the measure of importance from the model selected? For example, EGFR is less important in some models than in others. Is there a way to come up with a measure that describes the importance of EGFR regardless of the method selected?
Not necessarily, regardless of the approach. I mean, so getting at that idea of Lek plots, although, let me back up. So the Lek plots are interesting, right? Because if I look back at, and I got to go all the way back to the support vector machine or the neural nets. All the way back. Sorry, this is a long way back. Let's pick EGFR is a good one. So EGFR is showing sort of this, or we'll pick age and EGFR. So age is linear. EGFR has this kind of like you level off as you go up. So kind of keep those two in your mind, and then let's go look at how they looked for support vector machines, which did a similar thing. Because I really feel like those plots get better at the relation, what the actual relationship is. So if the relationship's nonlinear, it's hard to describe anyway. But okay, so here age is close to linear, but EGFR shows a very different relationship according to the support vector machines than what you saw from the neural networks. And so part of it, the reason it's so hard to consolidate across these models is they're modeling the relationships in very different ways. And so hard to say how accurate these are I think these do help. Like I will say, relative to the neural net Lek plot, the EGFR in the neural net Lek plot kind of went up and then leveled off. This is at least going up and not leveling off. It's coming crashing back down. But that would suggest that at least there's a nonlinear relationship. So I feel like they could help you in that way. And the Lek plots, more than the variable importance plots, would give you that kind of information. And again, relatively, there's not functionality necessarily to generate these plots for anything but the neural nets, but they're relatively easy to generate. You just generate a fake data set that fixes everything at the median and then varies the specific variable that you're interested in. So again, this would at least kind of tell you something about the functional relationship, whereas the variable importance, I mean, it went back to, so thinking about that in terms of just the rankings, what I would say is, okay, so here I'm relatively comfortable arguing that IL-2R alpha is important and probably EGFR, but as you get through, these other ones may be introducing more noise. And so I almost feel like you need to do variable selection and then apply these approaches. Now, I didn't do that in this case because it's only a data set of 10 and it's kind of fun. It's not interesting to look at 3 variables. It's interesting to look at 10. So I'm not sure that answers the question entirely, but I mean, it is tough because you will see if you play around with multiple models that you get different answers. So then you're going to, okay, well, does one really predict much, much better than the other? And I didn't look at prediction performance on these particular models. I was just kind of using them to do this process. Somewhere I have a prediction model for this thing. But in theory, let's say that like the AdaBoost ranked IL-2R alpha really, really low. Let's say that its prediction performance was much worse than everybody else. Okay, well, that you kind of want to pull that into play as well.
So Beth, that actually transitions really nicely into the next question. So there's a question about if you have a big data set where you have more predictors than observations, is there a way to eliminate features first and then proceed with modeling? And can you talk a little bit about the process of those decisions for big data sets?
Well, that's a whole several lectures in and of itself. What I would say is there are, going back to the idea of recursive feature elimination, so you can always apply recursive feature elimination. Now, there are lots of arguments in literature as to why that is somewhat problematic, but it's universal and you can apply it to any approach, and that would allow you to take yourself from a large set of features down to a smaller set of features. But what I would say is if that's of interest, and in big data sets, it generally is, there are, again, better than recursive feature elimination, there are other approaches to reduce the number of features that don't have some of these issues that recursive feature elimination has. In particular, I'm thinking about the fact that penalized regression type approaches have been adapted to be used for support vector machines and for neural nets. And I don't think for random forest. Random forest has all kinds of other feature selection approaches, which Dr. Spicer can tell you all about. So I mean, there are like method-specific approaches that have been developed. I do like the penalized approach because if I look at penalized regression approaches in a traditional regression setting, they perform fairly well. The same is true when we apply them in the support vector machine in the neural net setting, and they'll reduce the number of features. So they essentially apply a lasso-like penalty in fitting both of those models to select a sparse model, and then you could do feature importance once you'd selected the sparse model. So that way you're sort of doing it all within a unified framework as opposed to trying to pick a subset of features that you want to model and then modeling it. So it's actually sort of doing this simultaneously as you're developing the model. And those are good approaches and they're out there. And I think mostly available in R or MATLAB or Python or some other software platform.
Okay, I think we have time for one last question. I think I covered all the ones that came in, but definitely speak up or type in the chat if I missed one. And I should mention while we're waiting for if there's a final question, our next webinar is going to be on March 30th at 2 p.m. And we have two speakers. We have Jim Harner and his son Soren Harner, who are going to be talking about R versus Python for coding in data science. So be on the lookout for those emails. I probably will have it set up next week. Okay, so one last question just came in. So the question is, do you have any thoughts about the targeted maximum likelihood estimation approach to variable importance estimation done by the Vanderland group?
Ooh. I don't. I've not heard of it. It sounds lovely. I'd have to evaluate it. When did it come out? Can they, whoever it is, can they chat back and say when it came out? Nope, they chatted. Thank you.
Says for Shapely values. So look up the R package Shapely.
So this is, again, this goes back to, this is not what I'm familiar with. As I said at the end of this presentation, this is a very active area of research. Mm-hmm. I would also, it's interesting just thinking about a general comment. I've not necessarily seen head-to-head comparisons of all of the things that are available because there are so many things available. Usually people compare within approach and not across approach. I say that there are comparisons across approach, but then they'll pick a handful of either feature selection approaches or feature importance approaches. And we also didn't cover, there's other sorts of machine learning models out there. So you have things like Mars and relevance vector machines to get at continuous outcomes for these simple models like naive Bayes still can have some ranking of features and whatnot. So we only covered a small subset of the methods, which is sort of that got to one of the early questions about unsupervised approaches. So yeah, no, I'm interested. I appreciate whoever made that comment. Thank you for sharing that. Like I said, that's not one that's been on my radar, but I'm very curious about it now.
All right. Well, this was a wonderful talk. Thank you so much, Dr. Wolf. I definitely learned a lot, and I really enjoyed the discussion afterward. And thank you to everyone for attending.
Yes,
And
thank you guys.
we hope to see you again next month. All right. Take care, everyone.